Hello, in last class we have seen how Laplace equation can be converted into a difference equation, and from there we got a tridiagonal matrix, which is basically we are trying to solve heat conduction equation in a one dimensional or steady heat conduction equation. So, this class we will see how these equations can be solved, what is the most efficient way to solve these equations, and we will look into an algorithm named tridiagonal matrix algorithm. We had this problem when we were looking into matrix representation of physical systems, 1D steady conduction, rod where the governing equation is k d 2 t dx square is equal to 0 and the boundary conditions x is equal to 0, x is equal to 1. And we discretize this into number of finite points, where we finite number of discrete points where we got the difference equation for each point and the boundary condition at x is equal to 0, t 1 is equal to 0, at x is equal to 1, t 9 is equal to 1, and the finite points discretized equation, and first equation contains a t 1. So, we substituted t 1 in the first equation for example, and we also substituted t 9 in the last equation, and these two equations have changed actually, but in between equations remained 1, minus 2 and 1 for coefficients of the diagonal term and the next two terms. And what we got, we discussed it in last class, what we got is called a tridiagonal equation system. The matrix representation is this is a tridiagonal matrix. The diagonal, there is a main diagonal term, there is one super diagonal term which is the coefficient for the next points in the mesh, and a subdiagonal term which contains the coefficient from the previous points in the mesh. General form of tridiagonal matrix is this particular form, it was a symmetric matrix with minus 2 1 1 minus 2 1, and the coefficients, because we considered an uniform mesh, the coefficients were repeating in each row. However, in a general form it might not repeat, or we can get a general form of tridiagonal matrix where there are tridiagonals from row 2 to row n minus 1, and there are only 2 elements because the 0th element is not there or n plus 1th column is not there. There are only 2 elements in first and last row, and remaining all these terms are 0. Now, this is a very frequently arising matrix in lot of scientific computing problems, and we have to see how we can solve this. Interestingly, this is not only in not only comes from approximation of differential equation to difference equation. When we will do Krylov space method, we will see that some of the functional spaces will also transform to a tridiagonal system. There is a very important solution algorithm called generalized minimum residual algorithm, where or biconjugate stabilized biconjugate gradient method, where you will see tridiagonal matrices are coming in between the solution space. However, we have to see how we can solve this equation, and we have right now went through 3 different solvers. One is Gauss elimination, one is LU decomposition, and the other is Gauss-Jordan. These solvers, all these solvers for Gauss elimination, Gauss-Jordan, and also for doing the decomposition in LU decomposition, the number of operation for solving the matrix is of the order of n cube. So, if we have a 10,000 row matrix, the number of solution will be 10 to the power 12, number of operations will be 10 to the power 12, which is quite high. So, we will see is there any other method for this particular type of solution, and this is important because many times we will interact with matrices of similar form. So, solution of tridiagonal matrix system, Gauss elimination, LU decomposition or Gauss-Jordan, typically 6 order of n cube operation. For large physical problem, n may be very large for high accuracy. We have seen in the last class that as we increase n, dx reduces and the error reduces. So, for getting good highly accurate solution, n has to be large so that dx is small. However, there is one problem which you have also seen in last class, that there are round of errors. So, as we increase n, there will be high round of error, because each grid there will be some round, each operation is associated with some round of error. Also, as we increase n, the number of operations are of the order of n cube, which is very high. A Gauss elimination is a method for a general matrix, but it does not utilize the fact that here for this particular tridiagonal matrix form, which is this matrix is banded and sparse, and most elements in a row is 0. For example, if we apply Gauss elimination A1 if we apply Gauss elimination B1 C1 and then A2 B2 C2 A3 B3 C3. If we try to apply Gauss elimination here, in first step this A1 will be eliminated, but we do not need to eliminate anything here because this is already 0. Similarly, all these are already 0. When we will do the next step using B2, we can eliminate A2, but we do not need to eliminate anything here, it is already 0, it starts from A4 here. So, most of the elements in a row in 0, and we really do not need to eliminate all the terms below one particular pivot, only the next row below the particular pivot can be eliminated and we can get through with it. So, these few properties we can utilize and then have a specific algorithm for this type of matrices, and this algorithm is known as a tridiagonal matrix algorithm or TDMA. This is also known as Thomas algorithm, because there was a mathematician named Thomas who proposed this algorithm. So, we write down all the equations starting from equation 1 to equation n, and now and then what we will do something like a Gauss elimination step. First, we will eliminate the T1 from the second equation and then we will eliminate T2 from the third equation, so on. However, we will see that there is a recursive nature of this elimination process, and we will do that. So, we go for the elimination round and get a recursive relation, that equation 1, if we go back to equation 1 again, equation 1 gives us T1 is D1 minus CT2 by B1. Now, if we substitute this into equation 2, we will get A2 into D1 minus this, plus equation 2 was basically A2 T2 A2 T1 plus B2 T2 plus C2 T3 is equal to D2. This is equation 2. So, if we substitute this T1 into equation 2, we will get A2 into this particular term plus B2 T2 plus C2 T3 is equal to 0. So, this becomes an equation between T2 and T3. So, we can write something into T2 is D2 minus something into T3, and T2 is equal to D2 minus A2 B2 by B2 minus A2 C1 by B1 minus C2 by B2 minus A2 C1 by T3. So, few things we can see which are interesting here, that there is a general form that there is a general form that Ti is equal to some constant, say gamma I minus Ci divided by some constant beta I by Ti plus 1. This is a general rule for form we are getting for these two equations. Similarly, we can get similar expressions for equation 3, 4 to n minus 1, where we can get expression for T2 involving T3. For equation 4 we can get expression for we can for equation 3 we can get expression for T3 involving, this will be T3. T4 for For equation 4 we will get expression for T4 involving T5 and up to equation n minus 1 where we will get expression for Tn minus 1 involving Tn. So, equation I will give a general form Ti is equal to gamma I minus Ci by beta I Ti plus 1. This gamma and beta will change for each of the terms. So, equation I is converted to equation I prime. Similarly, equation I minus 1 will also have similar form Ti minus 1 is gamma I minus 1 minus Ci minus 1 beta I minus 1 Ti. Now, if we further substitute this Ti minus 1 into the original equation I, we will get the original equation is Ai Ti minus 1 plus Bi Ti plus Ci Ti plus 1 is equal to Di. So, this Ti minus 1 we got the expression for Ti minus 1 will substitute this into this particular equation, and what we will see that Ai into the expression for Ti minus 1 here plus Bi Ti plus Ci is equal to 0. So, we can rearrange it and write Ti is some constant minus something Ci by minus Ci by another constant into Ti plus 1. Now, if I compare equation I prime and equation I double prime, they are basically same equation. Ti is expressed in terms of Ti plus 1. We will see that the first term matches with this term, or we can probably see it here. This term matches this particular term, this term matches this term, and this term will match this term. So, I will see the that beta I is Bi minus Aici by beta I minus 1. So, if I know beta I minus 1, I can find beta I, and that is called a recursive relation, that one term is dependent on the previous term in that particular series. Similarly, once I know beta I minus 1 and I also know gamma I minus 1, which is from the previous equations, we can find out gamma I. So, gamma I is Di minus Ai gamma I minus 1 B2 minus Aici minus 1 by beta I minus 1, and comparing one I prime and I double prime, we get what is called a recursive relation. So, if we know one particular we know gamma 1 beta 1, we can find out gamma 2 beta 2, we know gamma 2 beta 2, we can find out gamma 3 beta 3, so on we can do it till gamma n beta n. Comparing 1 and 1 prime, we can write beta I is equal to Bi minus Aici minus 1 beta I minus 1, and so beta I is, if we know beta I minus 1, if we know beta I minus 1, we can find beta I, and if we know and gamma I, where this term is nothing but beta I here. So, if I know, I have earlier found beta I, so if I found beta I or I know beta I minus 1 and know gamma I minus 1, then I can find gamma I, and this is what we are seeking for a recursive relation. We will see why is it important. Till this point, this method is very much like a Gauss elimination. We are eliminating only the below pivot, next row below pivot element, and where each pivot elements the next row's first non-zero element. However, it does it only for the next row, it does not do it for the later rows, because the later rows have 0 at that element. The other terms below this row is already 0 due to tridiagonal nature of matrix. So, operations are much less than Gauss elimination operation for a dense matrix, and we will see this, the number of operations are of the order of n, if n is the total size of number of rows. These steps will go till n minus 1 equation, we will eliminate, we will express T n minus 1 as a function of, as a constant plus something into T n, and when we will get one equation for n minus 1, and we already have the last equation which relates T n and T n minus 1. So, we will get two unknown system, two unknown system by n T n minus 1 and T n using n minus 1 and nth equation, and we can solve that. However, we will try to find out a more elegant algorithm here. So, sorry. So, this is the forward step in TDMA. What is you got T I is equal to gamma I minus C I by beta I T I plus 1 and get what is T 1. Here we can find out beta 1 is equal to B 1 and gamma 1 is equal to D 1 beta 1, and then we have the recursive relations. Then we will have the recursive relations beta I and gamma I dependent on beta I minus 1 and gamma I minus 1, and we can calculate gamma 2, beta 2, gamma 3, beta 3, so on up to gamma n, beta n. Now, we will do the backward steps. The nth equation, we will start with the nth equation. Nth equation is the equation of n minus 1 and n, and we can write T n in terms of T n minus 1 in the nth equation. Now, T n is equal to gamma n minus 1 minus C n minus 1 beta n minus 1 by T n, which is using the recursive relation for n minus 1 equation which we got there. If we substitute this, this T n minus 1 into as this T n minus 1, which is coming from nth equation, we will get the value of T n. We will get an equation involving T n only, and we will get the value of T n as T n is d n minus a n gamma n minus 1 b n minus a n c n minus 1 by beta n minus 1, and gamma I is given as d I minus a I gamma I by I minus a I c I minus 1 b I minus 1, which is the general recursive relation for gamma I. If we compare these two things, T n is nothing but gamma n. So, as this is not needed, this is not needed at this stage. So, T n directly comes to gamma n if we compare these two relations. So, what we have done in forward steps, we calculate using the recursive, we started with gamma 1 and beta 1 from first equation using the recursive relationship, we came up to gamma n and beta n, and when we came up to gamma n, T n is nothing but gamma n. So, now we have to do the backward step starting from T n is equal to gamma n. The backward step will follow nothing but this particular relationship, that T I minus 1 is gamma I minus 1, which is already calculated C I minus 1 beta I minus 1 into T I plus 1. So, I will get T n minus 1. Similarly, I will get T n minus 2 once first I got T n, I got T n minus 1 using T n. Now, I will get T n minus 2 is gamma n minus 2 minus C n minus 2 by beta n minus 2 T n minus 1. Similarly, I will get T n minus 1 and so on, I will get up to T 2, because T 1 I already know, T up to I will get up to T 1, sorry, T 1 is not known to me, I will get up to T 1. So, now if we can summarize this algorithm, this will be probably of more help. We looked into derivation of the algorithm. If we can summarize it in form of the algorithm, this is the matrix equation, which is a tridiagonal matrix equation on which we are applying TDMA. We will start with beta 1 is equal to B 1, gamma 1 is equal to D 1 by beta 1. We will calculate beta and gamma for all other 2 to n using the recursive relationship. Now, I will set T n is equal to gamma n, which is the actual solution of nth point, and then we will use the relationship, which is again a recursive relationship. T I is equal to something gamma I minus C I by beta I T I plus 1 for n minus 1, n minus 2 and up to 1, and we will solve the equation. And this is the entire algorithm, which is a very straightforward algorithm. Only if we try to write a computer program, we have to write the expressions for gamma I and recursive relation for gamma I and beta I. There will be one sweep calculating all gamma and beta from 1 to n, and there will be one backward swing calculating all t's from tn minus 1 to t1. For a 5 into 5 matrix, the TDMA takes, this is order of n. So, just 10 operations, 5 operations forward step, 5 operations backward step, while a Gauss elimination takes 75 operations. So, it should be in any computer program, it should be more than 7 times faster than a Gauss elimination process. For a larger problem, it will be the efficiency can be much more evident, because say for a 100 into 100 matrix, TDMA will take few hundred operations, 200 operations, where Gauss elimination will take order of 1000 operations. So, it will be 10 times faster in that case, not 1000, 100 cube, 10 to the power 6 operations. So, it will be much faster, TDMA will be much faster, and TDMA is very useful algorithm used for tridiagonal matrices which occur heavily in very frequently in different scientific computations cases, especially in cases where one dimensional problems are involved. There are variants of TDMA. One is that instead of just being the tridiagonal, the central point, the diagonal point, the next point and the previous point, there is a something like a periodic boundary condition is there. There is one band which is away from the diagonal band, which is called the perturbed matrix, is associated here. For example, this is of the, you will see like these are the general diagonal forms. The first term will have one term here, one non-zero here, one non-zero here and one non-zero here. Similarly, the last term will have one non-zero here, one non-zero here and one non-zero here, which is near tridiagonal matrix, but it is perturbed from the tridiagonal space, and there is Sherman-Morrison formula. You can look it in detail, the formula is available widely in internet resources, which is a variant of tridiagonal matrix. There can be block tridiagonal matrices. Instead of having a tridiagonal matrix, there can be block matrices arranged in tridiagonal form. Like A is combination of several matrices arranged in tridiagonal space. We will look into block algorithms later of this course, later in this course. So, like B1, this is probably an n into n matrix. So, there are number, it is a large matrix and number of matrices arranged in block, and this block arrangement is tridiagonal, and using TDMA algorithm a variant can be obtained where the block matrices can be solved. These are not very difficult, very straightforward implementation of TDMA algorithm for these specific problems can help here. There is another interesting method which is called alternating direction implicit method, and this method is applicable for 2-dimensional problems. What is in a 2-dimensional problem? We have seen it earlier, that this is a Laplace equation in 2D which is converted into a we will get a matrix equation out of it into an equation involving variation of temperature along the points in both x and y direction. So, it has T I minus 1 j T I I plus 1 I j T I plus 1 j by dx square plus T I j minus 1 T I j minus 2 T I j plus T I j plus 1 by dy square is equal to 0. So, it is not of tridiagonal nature. If we try to look into the matrix, we can look into the matrix actually. So, this is the equation for each point, and now if I start numbering these points, like this is a boundary condition. So, which number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, so on. So, we will get that for this particular point, which is my 14th point now, we will get T minus 4 T 14 plus T 15 plus T 13, and this is T 5, and this is 5, this is 14. So, this will be 14 plus 9 23 plus t 23 is equal to 0. So, therefore, we can get a matrix equation with 1 1 minus 4 1 1 5 non-zero bands, and this will be like this. Sorry. We can get a matrix equation with this 5 non-zero bands. Sorry. Just a second. So, this is our order of delta x. Sorry. Yeah. So, we will get a matrix equation with this 5 non-zero bands, which is 4 minus 1 1 minus 1 4 minus 1 1 minus 1 minus 1 4 minus 1 minus 1. This is a general row of this matrix, and this is called a pentadiagonal matrix. So, we can see it is not a tridiagonal matrix. So, TDMA will be directly applicable here. So, what we have to do here, there is an application of TDMA which is called alternating direction implicit method, which will be applicable here. And this starts with this particular equation, and it will try to make it TDMA in a sense that it assumes there is a boundary condition for j is equal to 0, j is equal to 1 row. It assumes a guess value for j is equal to 3 row. For j is equal to 2 row, so there is a boundary value for j is equal to 1, j is equal to 1. There is a guess value which is assumed for j is equal to 3. So, for j is equal to 2, these values, the j plus 1 and j minus 1 values are already obtained from guess or boundary value. The unknowns remains only as of a tridiagonal form, which now all the points in this particular row, or say here we are solving in this particular row, all the points in j is equal to 2 row, all these points can be solved using a TDMA algorithm. And once this is done, now I have updated values for all these points. What is the present value of these points? Instead of guess, I will use this value here. I will have a guess value for this set of points and solve a TDMA at j is equal to 3. So, what I will do? I put an updated value here, I assume a guess value here, and solve for j is equal to 3 using TDMA. And similarly, we will do a sweep in y direction. So, we will solve for j is equal to 4, j is equal to 5, and each line, this is called a line solver, because each line can be solved using a TDMA. Once this is done, I have some updated value which are not final value, because we started with some guess value at certain points. We have some updated value of all the points, and then I will do a sweep in x direction. Similarly, I will assume guess value for one particular I, one guess value for one particular I here, one particular I here, one particular I here, and do a sweep, calculate all the values in the j direction, and then we will do a sweep. Similarly, value one particular I here, one particular I, calculate all the values in j direction. We have to do a sweep in x direction, and we will alternate these directions, continue this sweep with alternating the direction, once in x direction and once in y direction, alternating it until it converges to a final value when the solutions do not change. This is very useful, very quickly we can get solution much quickly than Gauss elimination or LU decomposition method. This is called an alternating direction implicit method. This is also an application of TDMA. This is an iterative method. Solution started with a guess value and converges to a final value which is close to the actual solution, and it uses TDMA at every step. However, this raises two interesting questions. What is an iterative method? We will start with a guess value and update the values, and we will do till it converges to the right solution. So, iterative method and convergence is a very interesting part in matrix solvers, and as said in the introductory lecture, that a plethora of matrix solvers are there based on iterative methods, and which look into first convergence of the solvers, which we will discuss at much later stage. Thank you.